Hello and welcome back. In this video we're going to prove the derivatives of inverse trig functions and hyperbolic functions. So let's start with example 3 where we're asked to prove the derivative of inverse sine is 1 over the square root of 1 minus x squared. We're going to start by just writing y equals inverse sine of x. Now, similar to how we took a first step with logarithms, where we rewrote the logarithms in terms of their inverse function, which is the exponential in that case, we're going to take these inverse trig functions and write them instead in terms of their inverses, which are the regular trig functions. And the way we'll do that is by applying the sine function to both sides. The sine function will undo the inverse sine function, so you'll just be left with x on the right side. Now, here what we could do is, just like with logarithms, use implicit differentiation. In other words, take the derivative of both sides with respect to x, even though we don't have y solved for explicitly. And that's going to help us take a next step. So I'm going to write down sine y equals and then x, but leave some space to write the derivative with respect to x. Now, it's implicit differentiation again because here the x is different from the y. The variable x is different from the variable y, so we're going to have to use implicit differentiation. And in fact, we're going to have to use a chain rule here because we have this y function inside of the sine function. So here's the derivative of the outer function, cosine y. And then what's the derivative of the inner function? It's going to be dy dx. Y is the inner function, and it's the derivative of the inner function with respect to x. And then the derivative of x is 1. So now we get, let me pull this over here to the right. So now we have dy dx is equal to 1 over cosine y. Now we want our final answer to be in terms of x. So let's rewrite y as inverse sine x. That's what y was to begin with, is inverse sine x. And now we've got this expression here, cosine of inverse sine of x. This may seem familiar from your trigonometry and pre-calculus classes, and you may have wondered why in the world you always had to simplify expressions like this. Well, here's one of the reasons. We're going to have to simplify, or we're going to want to simplify this expression so that it doesn't have these trig functions anymore. We want to write it using an algebraic function as much as possible, ones that just have exponents and possibly square roots and things like that. So the way we can do that, you might remember, is using a triangle. We can capture this inverse sine of x with a theta. So inverse sine x equals theta. So that sine theta is equal to x. Right? Just rewriting the inverse equation with the regular trig equation. Or in other words, you can think, if inverse sine inputs x and outputs theta, regular sine will do the opposite. It'll input a theta and output x. In other words, the inputs and the outputs switch when you write the inverse function. Now, this x we can write as x over 1, which helps us to think about sine as being opposite over adjacent in a triangle. So the opposite side would be x, and the adjacent, opposite over hypotenuse. So the opposite side would be x, and the hypotenuse would be 1. So what we can do is draw a little right triangle with theta in it. Opposite side is x, hypotenuse is 1. In that picture, definitely sine of theta is equal to x over 1, so it's just a visualization of sine of theta is equal to x over 1. And now in particular, we're interested in what cosine of theta is. Cosine of theta is adjacent over hypotenuse. So let's figure out what the adjacent side is. You can figure that out using the Pythagorean Theorem, and you'll end up with the square root of 1 minus x squared. So you can use the Pythagorean Theorem on that to get that leg, that unknown leg. So now cosine of theta we said was adjacent over hypotenuse, which is the square root of 1 minus x squared over 1, which we could just write over here as the square root of 1 minus x squared. And that completes our proof, because that's exactly what the derivative of inverse sine of x is. Or at least that's what we were told it is, and now we just proved it. All right, so hyperbolic functions, the way you can prove those is by the definition. At least for sinh and cosh, you can go back to the definition of hyperbolic functions. Remember, the definition of sinh is e to the x minus e to the negative x over 2. And for cosh, it's the same, but just a plus in the middle. So if you want to go and prove, like in example 4, that the derivative of sinh is cosh, what you could do is write the definition of sinh and take the derivative of that exponential definition of sinh. So we can start by writing the derivative of sinh is the derivative of e to the x minus e to the negative x over 2. So now we just have to take the derivative of that when we know the derivatives of the exponentials, because we just proved them not too long ago in the last video. So we can take the derivative of e to the x, which is e to the x. The derivative of e to the negative x, let's do that off to the side. The derivative of e to the negative x is going to involve a chain rule, right? We have a negative x function inside of the exponential function. So there we take the derivative of the outer function, which is itself, leaving the inside alone, and then multiply by the derivative of the inner function, which is negative 1. So here we get negative e to the negative x. Now, you have an extra negative in front of that e to the negative x, so you'll have minus negative e to the negative x after you take the derivative, which turns into plus e to the negative x. And then you still have this over 2. The over 2 is like a 1/2 coefficient that could be pulled out of the derivative altogether, so it's going to hang around. But if you look at e to the x plus e to the negative x over 2, well, that's exactly what cosh is. That's the definition of cosh. So this is cosh. Oh my gosh. Oh my gosh is right, because these are the derivatives you will be asked to prove on a quiz or a test. So derivative of tangent, secant, cotangent, cosecant, the inverse trig functions, the basic ones, sine, cosine, tangent, derivative of natural log, derivative of sinh and cosh and tanh. Those are the only derivatives that I will ask you to prove, the derivative shortcuts that you'll be asked to prove. But hopefully this series of videos have given you enough tools to be able to handle them. You'll find some of these in the homework assignments as well. And thank you, as always, for watching, and see you next time.